Okay, so tomorrow we're going to be doing a lab on projectile motion. And the best way for us to study projectile motion, because it's motion in both directions, is to launch something. So what we're going to be doing is we're going to be launching Q-tips, you know, those cotton swabs that you stick in your ears. We're going to be launching those at the from a straw. So we're going to take a straw like this, and we're going to stick a Q-tip in there. And when we blow it, kind of like a blowgun in the movies, we're going to blow that, and we're going to study the motion, which is hopefully a projectile of that Q-tip going outside of the straw. So we're doing a projectile motion lab. The objective is to study projectile motion and determine the muzzle velocity of a launcher. Now, the muzzle velocity in weaponry and in military is the velocity that a bullet leaves the muzzle or the end of the gun. Okay, so what we're looking for is the muzzle velocity of this Q-tip. So what is really the initial velocity? So that's what we're going to be studying. So in projectile motion, most of the time we have an angle. And so that makes it real difficult because we have an X component of the muzzle velocity going that way. We also have a Y component going this way. Well, if we can simplify this, then we can study this a little bit better. So if we can get rid of one of those velocities, either in the X direction or the Y direction, then we can solve some of this. Okay, so what we're going to do is we're going to start over here with the straw. We're going to put it at a set height, Y, which we can just measure using a measuring tape, and we're going to blow on the end of the straw. We're going to create it so that the only velocity that this Q-tip is going to have is only in the X direction. As long as there's no Y direction, then we can say that initial velocity in the Y direction is going to be 0, thus simplifying any of our equations. We know our measured delta Y. We know our initial Y velocity is 0. We know our Y acceleration is gravity in the negative direction, so we can easily find the time that it takes for this Q-tip to go from here to here. Once we find the time that that takes, we can go backwards using the delta X that we've measured from what we have and find that initial velocity or the muzzle velocity. So that's what we're going to be doing. Okay, so a little bit, and this is just a quick synopsis of the procedure that we're going to be doing. We're going to create a launcher using a straw and a Q-tip. Okay, so you have a Q-tip. You're going to, now for safety reasons and for sanitary reasons, one person should be doing the blowing on the straw. Okay, you're going to put the launcher on the edge of a table to create a constant value of delta Y. If you're standing here, then obviously your delta Y is going to be changing, and you want to leave it constant. So you're going to set a table and put your straw on there. Okay, this is going to take a little creativity because you also have to blow on it, so you have to make sure that you're not laying on top of that table. Okay, so you're going to put the launcher at the edge of a table. Then you're going to calculate the delta X using those kinematic equations. And this is going to be our actual value for delta X. So when we figure out our error analysis, we have our actual, and then we're going to have our experimental, which is going to be, we're going to blow the Q-tip and we're going to measure where it lands. Okay, so the way that we can find out our delta X more precisely is because this Q-tip is probably going to do a little bit of bouncing. At least it was when I was playing with it at home. It bounces a little bit. So one of the ways that we can be sure is we're going to put a piece of colored paper, like construction paper, and we're going to wet the end of that Q-tip. So it should leave a little wet dot, and so we can measure the delta X a little bit more precisely. So we're going to place a piece of paper on the ground where we've calculated our delta X to be. And then we're going to experimentally obtain the delta X by actually blowing and seeing where it hits. And that's going to be our difference between our experimental and our actual value. And we can calculate our error analysis for that. Okay, well now the question is, we want to sit there and we want to calculate the muzzle velocity. Okay, we're not really trying the purpose of our lab is not just to find out what the delta X is, but it's to find out what that initial velocity is. So we're going to go backwards, and be able to solve for our our initial velocity. Once we have that initial velocity, it's not going to matter whether we put this now straw at a projectile at an angle or whether we have it here. The initial velocity should be the same as long as the same person is doing the blowing at the end of the straw and keeping it at a constant pressure of the force. Okay, so now when we've calculated the muzzle velocity, we're going to redo the same lab, but we're going to be changing the angle. So here is 0 degrees, here being 90, we're going to vary it all the way along that way. And the way we're going to do that is we're going to use these bendable straws so we can blow on it still horizontal and only bend the tip up a certain degree. And what we're going to create is to be able to find out what is the difference between when we vary theta and what happens to our range of our projectile. So it's going to be an interesting lab. We're going to be blowing these Q-tips all over the place. It's a good lab for us to figure out exactly how projectiles are and use those equations to solve some real values that we can measure. We will have a workup on the lab, and we'll be working on it in the next couple days. So we'll see you tomorrow, and you don't have to bring any of your Q-tips. Leave them at home, leave them in the bathroom, and you don't have to worry about the straws. I'll provide those too. So we'll see you tomorrow.